We'll consider in this section whether you can actually measure a single ion activity coefficient. What we talked about so far is measuring mean activity coefficients and mean activities and mean concentrations, a geometric average. But can we actually measure a single ion activity coefficient, and if we could measure it, would it mean anything? I use the word maybe. Now, when I gave this lecture last year, I said, yeah, this is how you do it, and so on. But then I got to reading the literature, and maybe not. Let me give you some background. So here's an article by Guggenheim from 1929. He was quite a good thermodynamicist. And here he's saying that you cannot measure individual activity coefficients for individual ions. All right, so I try to get the see if I can get up here where he actually says that. Yeah, so here it is. The general, maybe I'll make that a little bigger in case you're looking at this on your iPhone. All right, here's the bottom line, which is almost the bottom line of this page. The general principle, why measuring activity coefficients of single ions, or even talking about activity of single ions, is incorrect as follows. The electric potential difference between any 2 points in different media can never be measured and has yet to be defined in terms of physical realities. It is therefore a conception which has no physical significance. Okay, well, and everybody if you look at introductory physical chemistry texts, they say, no, you can't measure activity coefficients of individual ions, blah, blah, blah. But in fact, maybe you can. Let's actually define what we mean by the activity coefficient of a single ion. For example, if you have, in the previous example, we had H plus and Cl minus. Well, just let's define the electrochemical potential of H plus to be the standard state electrical chemical potential of H plus RT times the natural log of the, actually just write it this way first, the activity of H plus. And that would then be the electrochemical potential of H plus standard state plus RT times the natural log of the activity of the single ion H plus times the concentration of the ion. What do you want to use standard state? How about molal concentration of H plus? All right, so there is a definition of the activity coefficient of a single ionic species. All right, well, let's see. So here we go. Here's a Journal of Physical Chemistry. That journal's not too shabby. That's an ACS journal, American Chemical Society journal. And here talking about single ion activity, experiment versus theory. All right, so here it is. Maybe make it a little bigger so you can see it. So this is published last year, 2012. And even though from a straightforward thermodynamic standpoint, only the mean ionic activity has a clear, undisputable physical meaning, there's been a literature yearning for almost a century to measure single ion activities and so on. So he says, yeah, maybe you can't, but nonetheless it's useful. So let's actually measure single ion activity coefficients. And what people normally do who do this are use what's known as ion-specific electrodes. The most common example of that would be a pH meter. So a pH meter has an electrode. You put it in the solution, and it measures hydrogen ion concentration, measures the pH, or hydrogen ion activity. No, yeah, that's right, because when you measure electrical stuff, electrochemical stuff, you measure activity. So we've been essentially using the concept of pH and pH meters and pH electrodes. We've been using for many, many years the concept of a single ion activity and single ion activity coefficient. But according to Guggenheim, 1929, that has no physical significance. So Guggenheim's argument is the following. in order to talk physically meaningful, what you would have to have is a beaker full of H plus ions. The problem is you can't go down to the stockroom and buy, say, a bunch of H plus ions. You always have a counter ion, Cl minus. So what you have to maintain in this macroscopic solution is electroneutrality. So electroneutrality. So you always have to have the negative. So you can't really talk about just one without having to talk about the other. That's his first point. The second point, remember we defined electrochemical activity, electrochemical potential. That was defined as the chemical potential of some species plus ZF times the electric field. So the electrochemical potential, which you measure, is composed of two different parts. You only have one measurement, so you can arbitrarily divide up the electrochemical potential into some chemical potential due to concentration and some electric stuff that has to do with the charge. But you have like sodium ions. The sodium and the ion, these are two that are linked together. You can't pull off the plus and just have the sodium. They're one and the same. And so Guggenheim is arguing that you can't really separate out the chemical and the electrical part of the electrochemical potential. It's arbitrary. You can easily, by convention, assign different amounts to there, and therefore it's you can't talk about individual contributions to electrochemical potential. But nonetheless, this article was published in the ACS journal, pretty good journal, and talk about single ion activity. Well, as scientists often don't play all the way nice all the time, so here is a reply to that. Here is go by here first, the comment on single ion activity. So here's this guy who's saying that well, what you just saying to the guy who published the article, the previous article, that it's not really, you shouldn't really, let's see his bottom line here. Let's make this a little bigger. We'll talk about Debye potential and Debye-Huckel theory in the next part of this lecture. But what he's saying is that it appears that the theoretical activity coefficients for single ions are mathematical constructs that are hardly meaningful from the physical point of view. Okay, well, so you can talk about them, you can calculate them, but they don't mean anything. And then when a journal receives a comment on an article, meaning you're criticizing the article, they invite the author of the original article to reply. So here's Frankel's reply to the comment on his original article. And, you know, it's kind of interesting reading here. Zarubin accuses me of dismissing the phenomenological interpretation, blah, 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 blah. So I guess this guy Frankel's a little pissed off that Frankel did that. And then what he does is he goes on and starts waxing philosophically. So Zarubin says that, well, you know, it has no physical meaning, the model's useless, and so on. So what this guy does is quote philosophy here, which on building a theoretical model, which the guy says doesn't mean anything. So this is what it means. It involves conceiving a model that contains only the essential features of the real solution. If the model yields the wrong answers, then one tries again by changing the imagined model until one arrives at a model, the theoretical predictions of which agree well with experimental observation, and so on. So he's defending, based on philosophical grounds, the fact that even though you know, it's a useful model, even though you may not have any physical reality, as most models are only approximations of physical reality. And he goes on to say, if this guy's validity requirement were a prerequisite in theoretical modeling, no theory could have ever been devised. Okay, so that's recent. That was last year, going back and forth. So to answer the question, that's why I said, can single ion activities be measured? I say maybe. Depends on what side of the philosophical argument you're talking about. Well, let's actually go ahead and say we can measure activity coefficients of single ions. And I'll show you how you can do that. And actually I did this when I was doing I submitted a paper, and I was measuring something as a function of chloride concentration, and the reviewer of the paper sent it back saying, well, you know, you really should be plotting this not as a function of chloride concentration but chloride activity. So I said, oh, I guess I have to measure activity. So I went ahead and measured activity by this way. I'll show you what I did for that. And my calculations, by the way, this should be same as last time, 50.9 millivolts. All right, so here is the system I did to actually measure the activity coefficient. I had 2 beakers, and it was separated by a salt bridge. Here's my salt bridge. And over here we had a sodium chloride solution, and over here we had a sodium chloride solution, and here I had a silver chloride electrode. Here it is. And so I coated this. Actually, I got it from a pH meter. They use oftentimes, or pH electrode oftentimes use silver chloride as reference electrodes. And here's another silver chloride electrode here. Over here, I put 1 molar concentration of sodium here. And here, let's say I want to measure the activity coefficient of, say, a 0.15 molar solution. So this is known as a concentration cell. Let's write down the Nernst equation for this. It's non-equilibrium, 1 molar, 0.15 molar. You have a concentration gradient of chloride across there. Cell voltage will be the standard cell voltage plus, sorry, there should be a minus. I'm going to forget that minus there. Minus RT over NF times the activity, times the natural log of the activity. Well, actually, let's write down what's going on here. On the, say, side 1, and this is side 2, on side 1, we'll have the reaction silver chloride, make this a reduction reaction, solid, goes to silver solid plus chloride aqueous. This is water solutions. And this takes 1 electron. You take the 1 electron, the silver plus makes silver solid. And on the other side, it's the same reaction. 1 electron, we'll write as reduction, goes to silver plus Cl minus aqueous. So on side 2, this concentration is 1 molar. On side 1, this concentration is 0.15 molar. So we have a concentration gradient. So this is a concentration cell. And note that you have the same half reaction, so E0 is 0. And N, we have 1 electron. So RT over F at room temperature, we said was 0.02568 in SI units. It's RT over F, where N is equal to 1. I forgot to write down what this is. So this would be the logarithm. Let's do 1 over 2. So the logarithm of concentration of chloride inside 1 over the concentration of chloride inside 2. Actually, sorry, we're not quite there yet. So let's talk about activities first. So the activity of chloride inside 1 divided by the activity of chloride on side 2. That's not a square, those are sides. So RT over F times the natural log. Now let's make the activity coefficient. So this would be gamma of the chloride single ion activity coefficient times the concentration of chloride, and this has to be in molar because we're using a standard state, although standard states cancel out, divided by look, this is at 1 molar. That's the standard state. So that's just 1. So if we measure the cell voltage, that is just equal to minus 0.02568 times the natural log of the activity coefficient of the single ion minus times the chloride concentration, Cl minus. All right. So you actually do this. Chloride concentration given in the problem is 0.15 molar. So you calculate this out, you find that the activity coefficient of chloride is 0.92. So there's an experimental setup in which you can measure the activity coefficient of a single ion by making one side of the cell be standard state so that activity goes away. All right, so, but again, you have to keep in mind that it's still a debatable question of whether you can actually, whether the activity coefficients of single ions you do calculate actually mean anything. Oh, by the way, this is an interesting little historical note. When I actually went to look up some information about electrochemical potentials and activity coefficients and so on, I went to the National Institutes of Standards. That's a government-run site, and said that, that all the stuff there. Well, as you may or may not know, the government has shut down. And this is the what you get if you try to go to the government page. NIST, National Institute of Standards Technology, is closed. Affiliated websites not available due to a lapse in government funding. The National Institute. So there you go. That's one of the scientific fallouts from the lack of government funding, which happened last Tuesday, I guess. All right, well, just a historical note there.